Hi, my name's Fred Zelt. I'm a geologist living in Pittsburgh, and I'd like to share a talk that was delivered a week ago on March 30th, 2025, at the Geological Society of America meeting in Erie, Pennsylvania. So let me get the screen share going. This is a talk that was presented uh, on behalf of Bob Jacoby, my co-author, and me, about compressional structures exposed along the shore of Lake Erie in western New York. Our study area is in the Devonian outcrop belt, north of the limit of glaciation, along the eastern shore of Lake Erie. This shaded relief map shows examples we will see of interpreted shallow form pop-up structures in the glaciated plateau and in the unglaciated plateau near Pittsburgh. For comparison, we'll look at compressional structures that were probably caused by shear beneath glaciers in western New York, Pennsylvania, and northern Ohio. Then we'll see a good example of deep-formed Alleghanian compressional structures in Devonian shale bedrock in northern Ohio. Here are examples of pop-ups in quarries and fields. They're typical buccal folds with planar limbs and irregular axial and crustal fractures. The orientation of the fold axis can vary. In quarries, they occur in both glaciated and unglaciated areas. This is a good example of shallow form pop-ups that are kilometers long on the floor of Lake Ontario south of Toronto within the glaciated plateau. We'll see submersible images of the pop-ups, look at seismic profiles across one of the pop-ups, and then look at an enlarged bathymetric map. Seismic profiles show onlap of recent sediment onto the pop-ups, and the study authors were able to determine relative timing of the pop-ups. The submersible images and sketches look a lot like pop-ups found in quarries and fields. In this enlargement of the map, you can see pop-ups with multiple orientations. The ones labeled 1, 2, and 3 are roughly parallel and are the oldest of the pop-ups. Younger pop-ups have different and more variable orientations. The older pop-ups are more or less parallel to isobases from glacial Lake Iroquois and were thought to have formed by glacial loading, such as in the area of a peripheral bulge. As the glacier retreated, the peripheral bulge retreated, glacial rebound effects diminished, and the horizontal stress field would have changed. The younger pop-ups have different orientations, potentially including more influence from underlying structures. This example helps illustrate potential causes of variable orientations of small post-glacial pop-up anticlines. Next, we'll look at a map of the area outlined in red here. This map was compiled from multiple sources. The dashed lines indicate large surface anticlines formed by Alleghanian tectonism in the area of Silurian salt. The other lines in the gray map area show cross-strike fractures or joints, which were interpreted to indicate the orientation of Alleghanian compression in the nearly flat-lying plateau strata. Alleghanian compression in our western New York study area was oriented northwest-southeast. The lines outside the gray map area show generalized orientations of joint sets. As has been said by many researchers, the joints likely formed during deep burial and were influenced by Alleghanian tectonics, perhaps with enhancement during later uplift. Moving to the lakeshore, we will start looking at a compressional structure near Ripley, New York. The red line and black arrows show the direction of compression that's indicated by a structure at Ripley Beach. Here's an illustration from the lakeshore near Ripley from Hall 1843. There's a nice compressional structure with a thrust fault and related fold. G.K. Gilbert studied the Ripley structure to better understand small anticlines at the surface in western New York and northern Ohio, like the ones in fields we saw earlier. He noted that the structure well exposed in cross-section in this lakeshore cliff diminished with depth within the outcrop. This structure convinced Gilbert that the other small post-glacial anticlines formed shallow, or in his words, were superficial, without deep structural roots. Here's what may be the same structure, well exposed in cross-section and publicly accessible at Ripley Beach, New York. The structure has a thrust fault at the bottom with the same vergence as in the 1843 drawing, with a nice fold on top. Here's another view of it with close-ups. The basal thrust fault has gouge. The thrust fault dies out to the left and right. There's no sign of it several meters in either direction. The nature of the fold changes vertically from a rounded fold cored by gouge above a basal thrust fault to a buccal fold with an apparent void in the upper blue box, reminiscent of buckle folds we saw in quarries and fields. We'll look at an interpretation of the outcrop inside the yellow box. In red, there's a basal detachment with overlying gouge and at least one other detachment shallower. Bedding parallel slip may also accommodate vertical changes in displacement, fold height, width, and style. The sense of vergence alternates, and this structure may help illuminate the formation of stacked thrust faults with opposing vergences we'll see in other localities. We encourage others to study this excellent and likely historic outcrop on a public beach. For example, more detailed study might identify whether the structure formed all at once or sequentially in stages. Next, we will focus on an area along lakeshore cliffs near Frank Lloyd Wright's Gray Cliff. The area near and to the southwest of Gray Cliff, shown by the red box, will survey a dozen compressional structures to get a sense of variation in style. The orientation of compression indicated by thrust faults and folds exposed in lakeshore cliffs in this area rotates. The progressive rotation suggests to us that these structures are related even though they differ in style. The first three structures occur on a publicly accessible beach, Point Breeze Beach. There's a 1.35 meter long walking stick for scale. These are all relatively small, subtle features. Here's an interpreted photo with the thrust fault that I think was described by Grabeau in 1898. The inset box shows a fold on top of the thrust fault with an apparent void in the axis. There's very little displacement across the fault. Nearby on the same beach, there are 5 buckle folds. The buckle folds indicate and have an identical orientation of compression, which is only 10 degrees from compression indicated by the thrust fault and fold. This buckle has an irregular axial fracture, which may be a bit open too. Here's another one. You can see that organic-rich shale at the top is more brittle than the more clay-rich gray shale below, but both are part of the buckle fold. Next, we come to a place we call Broad Fold Beach. The white line shows that there's a broad open fold a few feet in amplitude. There's a 2-meter bar for scale. The overlying shales are folded too. You might wonder how such a broad open fold is related to pop-up structures. This is just down the beach, and it indicates an orientation of compression within 10 degrees of the orientation of compression indicated by the broad fold. This small faulted fold with pop-up characteristics and the broad fold probably were caused by the same regime of horizontal and vertical stresses, and both structures are part of the progressive rotation of compression in this area. On the other side of the broad open fold, there's a bedding parallel fault with gouge and upward splays exposed in the lakeshore bluff. The relationship of the gray fault gouge with joints in black shales indicates that the fault gouge, at least in part, was in place after joint formation. As mentioned before, the joints probably formed during deep burial and Alleghanian deformation. Some of the joints extend through the fault gouge, so maybe some of the joints were reactivated or enhanced later, perhaps during episodes of uplift, including glacial rebound, as suggested by Lash and Engelder. Bedding parallel faults with gouge occur in both deep and shallow structural settings. These structures await more detailed study, which we invite others to conduct. The next locality is a place we call Valtz Cove. There's a concretionary layer in the bottom part of the upper Devonian shale outcrop. There's no vertical displacement of that. The lower fault soles out, then it totally disappears just like the other pop-up faults. There's no trace of it to the left or right. These faults are well-defined, vertically stacked, and with opposing vergences. We'll take a closer look at both faults. The lower fault has a drag fold that's almost a kink band. I think Grabeau in 1898 described this structure as including vertical bedding. As the fault continues down and to the right, it's overlain by a gouge before it completely disappears. The upper fault is a little harder to see from the beach, but it has fault gouge and the overlying shale is folded. Here's another one without many features characteristic of a pop-up. There's little apparent displacement and the fault dies out downward and laterally to the left. It looks like it's part of the same system because you can see that compression indicated by the red line on the map here at Suncliff Point is in the same orientation as nearby faulted folds that have more features characteristic of shallow formed pop-ups. This is a place we call Fletcher Cove after a description of folds here by Grabeau in 1898. This lakeshore outcrop is 1.5 miles southwest of the mouth of 18 Mile Creek, New York, which fits descriptions by Grabeau and Hall. You can see that the Middle Devonian Tichenor limestone at lake level in the foreground rises about 4 feet from left to right. In the 1800s, they described a thrust fault at the Tichenor level. The area that would be faulted at the Tichenor level was covered when the structure was rediscovered last summer, so we can't verify that there's a thrust fault at that level. But in the Upper Devonian shales in the bluff, there clearly are 2 thrust faults with opposing vergences. So there may actually be 3 stacked thrust faults with alternating vergences. Here's a closer look at the Upper Devonian shales. The circled hammer is in the same place in both photos, which were taken from different vantage points. There are folds below and above the middle fault, and there's a fold above the upper fault. This is the last of the compressional structures we'll see from the lakeshore area near Graycliff. This is in Middle Devonian shales. The calcareous Bethany marker bed is offset by a couple of feet here along the edge of 18 Mile Creek near its confluence with Lake Erie. The interpreted fault is highlighted. There's a small fold that gives us an orientation. This was one of the first of these structures we saw in the area, and the orientation of interpreted compression made me think it was likely a product of Alleghanian compression. That's still possible, but the orientation of compression here fits with the progressive rotation of other features that more clearly include shallow-formed post-glacial pop-up structures. We think there's still more to learn about these structures, and more structures to find in Devonian shales along the lakeshore, especially outside the study area. The lakeshore structures, well exposed in cross-section, helped Bob and me think about recognition criteria for pop-ups, having a void or an irregular axial fracture in a buccal fold, stacked thrust faults with opposing vergences, which can have gouge. And at Ripley Beach, there's fault gouge below the fold with a very different overlying fold, clearly a shallow-formed post-glacial feature with no tie to deeper structural roots. Shallow-formed pop-ups occur in valleys, too. Valley or stream anticlines are well known from many parts of the world, for example, in the central Grand Canyon, where the base of the canyon is in Cambrian shale. Hall recognized them in the 1840s in western New York, and many researchers have found them in stream valleys incised into Devonian shale in New York, northwestern Pennsylvania, and northern Ohio. Here, Hall shows an anticline under a stream valley that was incised into Devonian shale bedrock of western New York after Pleistocene glaciers had retreated. Incision increases vertical load and enables compressional structures, including pop-ups, to form in shaly bedrock in and beneath stream and river valleys. Seeing pop-ups well exposed in cross-section in the lakeshore outcrops caused both Bob and me to look back at places we had seen in the past. Here's an example from Bob from Allegheny County in the plateau area of Devonian shale bedrock in western New York. Within narrow incised valleys, there are buccal folds or pop-ups associated with valley incision. The 17 buccal folds indicate compression in every map orientation, and it might have been tempting to come up with different tectonic or underlying structural reasons for those orientations. But when you look at the orientations of reaches of streams where those folds are located, 16 of the 17 folds are parallel or subparallel to the stream valley. That's a hallmark of stream valley anticlines. In this case, the stream reaches commonly are oriented parallel to regional joint sets or old structural features, so that the young shallow-formed pop-ups aligned with incised valleys could also be aligned with old pre-existing structures. Fall Run Park is a public space in the unglaciated plateau near Pittsburgh that I've used for teaching geology for several years. After learning from the lakeshore pop-ups, I realized that odd features in Pennsylvanian strata at Fall Run have the hallmarks of stream or valley pop-ups. The structure shown has planar siltstone limbs and an open zigzag axial fracture. It has an orientation of compression consistent with Alleghanian tectonics, but it's also exactly correct for a stream valley anticline in this narrow, young, V-shaped valley. On the map, you can see that there's a second fold in siltstone a little farther north with a slightly different orientation that fits the valley there better than it fits Alleghanian tectonics. Thinking about recognition criteria of post-glacial shallow-form pop-ups in the lakeshore outcrops opened our minds to the possibilities of pop-ups in other places, including unglaciated areas. Some compressional structures in Devonian shales of the glaciated plateau were probably formed by shear of overlying glaciers. This slide shows good examples of structures formed in several parts of the world by glacial shear of sediment. These structures tend to be very asymmetrical. The amount of strain decreases rapidly with depth because the structures are formed by shear at the surface. These structures can involve bedrock, they can involve till, and they can involve both bedrock and till. Here's a classic panoramic cross-section from Hall on the Erie lakeshore of western New York. The close-up shows the relationship between Devonian shale bedrock, broken bedrock, and flaps of bedrock with till underneath and on top. Bedrock breccia is associated with these subglacial structures. The structures are very asymmetrical, with the glacier having flowed from left to right. This good example was exposed during excavation of a power plant foundation in northeastern Ohio. Here you see deformed Devonian shale on top of undeformed shale bedrock. There are asymmetric folds with thrust faults, and the author noted that the amount of deformation decreased downward. The deformed bedrock is overlain by what was described as clay with clasts of shale bedrock, or in other words, bedrock breccia. The bedrock breccia grades upward into a typical till with clasts that come from farther away. The orientation of compression indicated by the structures was consistent with glacial flow based on striations and the regional context, left to right on the cross-section. Here's an example I first saw only 3 weeks ago on the lakeshore in Pennsylvania near the border with New York. The Upper Devonian shale bedrock with thin sandstones was folded with two panels that dip to the right and terminate to the left at a thrust fault. An asymmetrical recumbent fold in shale layers and gouge indicates the direction of thrust fault movement. Bedrock breccia and gouge above the fault on the left and bedrock breccia on top of the folded bedrock on the right grade upward into gray till with bedrock blocks, then typical gray till with exotic clasts. The till is overlain by flat-lying, undeformed brown sand and silt that are probably proglacial sediments. This could be a flap of bedrock deformed by shear at the bottom of a glacier. The south-southwest orientation of compression here is consistent with the possibility of glacial shear. Here's an example of deformed Upper Devonian shales in the glaciated plateau of northern Ohio that illustrates the hallmarks of deep-formed Alleghanian tectonic features. There are multiple stacked imbricate thrust faults. There's an asymmetrical recumbent fold that includes overturned beds. The direction of compression here is consistent with Alleghanian compression, northwest-southeast. Many of the folds and faults trend across, not parallel, to the incised stream valley, unlike valley anticlines. Here's a summary of our observations so far. Shallow form pop-ups tend to be fairly symmetrical vertical structures. They can be stacked, they can include voids, and they can have little apparent vertical displacement away from the main structure. The faults die out with depth. The structures can include deformed quaternary sediment. On glaciated open terrain and in quarries, they form shallow with little overburden. Orientations of compression can vary, as we saw beneath Lake Ontario and in the Western New York Lakeshore Study Area. In valleys, there can be preferential orientation parallel to the valley. In quarries, there can be a preferred orientation that fits present-day maximum horizontal stress, although at quarry edges near high walls, the horizontal stress field and resulting pop-ups can have different orientations. In valleys, the compressional structures can be best developed where the valley is oriented perpendicular to the present-day maximum horizontal stress. Sub-glacial compressional structures tend to be asymmetrical with recumbent folds. They occur at the top of bedrock and strain dies out with depth. There's an association with bedrock breccia, and they can be overlain by undeformed sediment, as we saw with proglacial sand and silt. In deep-formed orogenic structures, hallmarks include asymmetrical folds that can include recumbent folds and stacks of more than two imbricate thrust faults. Faults continue as far down as observation allows. The apparent displacement can be large, and the direction of compression fits orogenic stress. As we think about possible origins of compressional structures in Devonian shales of the plateau, we need to be mindful of other types of structures, such as those formed by soft sediment deformation. We hope you've enjoyed this foray into Western New York lakefront geology, and we hope other folks will study and learn from these structures. We've put the GPS coordinates for the localities shown in this slide set, but they're also published in the Gray Cliff chapter in Geological Society of America Field Guide 71, just published. Also, there should be a slide set hopefully posted with the abstract in the talk that was delivered March 30th at the GSA meeting in Erie. So that should show up on the website. And there's a possibility of an article in Pennsylvania Geology about these post-glacial pop-up structures. We hope to learn from continued work, including work by others on these structures. And we look forward to learning there. Thank you.